So we'll try to look for alternative arrangements for following installments in the series. So it's my pleasure to welcome you all. It's a particular pleasure for us here at CAMS to be holding this first live seminar colloquium after a very, very hard couple of years, in which we also discovered the wonders of online interaction. Though this has been both a benefit for us, but we certainly have missed the live component of interaction around mathematics, and we hope that this will be the first in a series to follow with minimal interruptions, hopefully. So it's also the first in a series of what we're calling the CAMS colloquia, in which we invite mathematicians, talents who are working here in Lebanon, but also visitors who happen to be passing through Lebanon, to come and give us an overview of their field of interest with a non-specialist audience in mind. So definitely mathematically inclined, but certainly non-specialists in the particular field. So an overview of that field leading up to results that are of a more technical nature, but again described for that broad audience. And it's my pleasure to welcome our colleague, our dear friend, CAMS associate, member of our steering committee, and definitely one of the pillars of the popularization of fields of mathematics through CAMS, Professor Ayman Kachmar from the Lebanese University. Ayman has been instrumental for us at CAMS in piloting thematic programs, having structured a beautiful program on the mathematical physics of condensed matter over a few months of mini courses leading up to a conference, an international conference held primarily online, bringing experts in mathematical physics from a variety of disciplines, but in one way or the other, all working around aspects of spectral theory and its applications to physics, which is at the core of Ayman's interests. So Ayman is a professor at the Lebanese University, having finished a PhD in 2007 at Paris Sud with Bernard, was it? Bernard Helffer, a long-standing collaborator of his. And he is essentially a specialist in spectral theory and its application. And today he will be telling us about essentially looking at the magnetic edge and the semi-classical eigenvalue asymptotics associated with a limit where magnetic fields undergo variations over very small length scales. So this is a very interesting limit. Here, Ayman is showing the usual knack he has of revisiting problems which required some fairly advanced mathematics and showing interesting ways to get at the heart of the problem, generally simpler ways. Thank you very much, Ayman. I'm very much looking forward to your talk.
Thank you very much, Jihad, for the introduction, and welcome everyone, and thank you for attending the talk. So the idea for me was to give an introduction on this subject, on eigenvalue asymptotics, on semi-classical eigenvalue asymptotics, to non-specialists, and that's why you will see many examples. That's why you will see many examples before heading to the statement of precise theorems and original results. So the magnetic edge part will be the last part of the talk. So I would like to start by motivating some questions on the subject. So the story begins from quantum mechanics, where we ask the question of computing the energy levels of an electron moving in a magnetic field. So there are two subjects here, the energy levels on the one hand and the magnetic field that enters to the play, because at the early developments, the energy levels were computed without a magnetic field. And then we understood what happens with a magnetic field. And if I want to translate this question to mathematics, it's a question in spectral theory, how we find the eigenvalue of a certain operator. So the energy levels will correspond to eigenvalues of a famous operator, the Laplace operator. It's very famous in the theory of PDEs. But we add to it a term to model the magnetic effects. And when we talk about spectral theory, so it's something that begins with linear algebra. We have some operator, some linear function A, and we would like to find scalar quantities lambda that we call eigenvalues. And we would like to solve the equation, finding a vector u, which is non-null, such that the equation AU equal lambda u is satisfied. So it begins with linear algebra with matrices, but when we want to discuss it and at the quantum mechanics level, we need to move from linear algebra because we introduce infinite dimensional spaces, as we shall see later, because this operator A is going to be a differential operator, so it will act on an infinite dimensional space. So the magnetic edge story is that somehow in the years in the beginning of the 20th century, those magnetic fields were observed experimentally. So these are magnetic fields that vary on a very short scale. They vary rapidly, and they are modeled as step functions. So in nature, quantities vary smoothly, but because this quantity varies very quickly, it's modeled as a step function in a strange way. And it creates this magnetic edge that we will see later on. What about the semi-classical asymptotics? Because if we remember that the beginning of our story starts from quantum mechanics. So in quantum mechanics, we study electrons, we study atomic scales, and at the atomic scales, the scale is very small. And that's why we will see a parameter that amounts to this very small scale that we will call the semi-classical parameter. And when we consider its limit as it approaches zero, this will be a singular limit because it's not a continuous limit. We cannot simply replace the parameter by zero and obtain the result. When we replace it by zero, we lose a lot of information. We lose the interest of the problem. And things will be clearer in the next slides. So part one of this talk is to understand the simple examples. First of all, we understand the model. What happens when we don't have a magnetic field? So originally, the problem starts with the presence of an electric field. So we suppose that we have an electron that moves in the free space under an electric field. And unlike classical objects, electron cannot have its energy, cannot select its energy in a continuous manner. It cannot collect any value as an energy, but it has to choose from a set of values, from a discrete set of values. And these discrete set of values are the energy levels. And that's the difference between classical physics and quantum physics. So the energy here is not a quantity that moves continuously. It's a quantity that is selected from a discrete set. And so these energy levels in physics are in mathematics, as I said before. These are eigenvalues of an operator. So the operator at this level is, so you see several parts of the operator. There is this h squared. So h is the semi-classical parameter. It's a positive parameter. I will talk more about it later. And there is this Laplace operator. I think all of you took calculus courses, so I think you remember what the Laplace operator is. It's the free Laplace operator. And we add to it a function, a multiplicative function, v. So everything here has its meaning, particularly v here. So v here models the electric field. So it's a potential that models the electric field. So the gradient of V, if I'm not mistaken, if I'm not missing something from physics, corresponds to the electric field we have. And this semi-classical parameter H, the positive parameter, is very small because it models the atomic scale. So at the atomic scale, what we expect, so a single electron, say, you expect its energy to be small. You expect that it moves on small scales, and that's why we introduce this parameter H and we take it very small. At this time also, I can explain why the limit is singular, because if you put H equals 0 here, you lose the Laplace operator. So what we will have at this step, so when I write something on the board. So if we return to the eigenvalue problem, so we will have we are looking for a scalar quantity lambda and a function u such that this equation is satisfied. And as we see, this is a PDE. This is a differential equation. So if you replace h by 0, you will forget the differential part of the equation, and then you lose a lot. You lose the character of the problem. So that's why this is a singular limit. I can't simply say that when I send h to 0, I will forget the Laplace, the differential part of the equation. Otherwise, it will be no more a differential equation. And that's what adds to the difficulty of the problem, in fact. So I will start with the first example. It's a very simple example called the harmonic oscillator. And there is reason why we choose this name. So the harmonic oscillator is, it comes from classical mechanics when there is a spring that oscillates with some Hooke's constant. And the quantum mechanical analog of the harmonic oscillator is this differential operator that I will introduce now. And to simplify matters, I will suppose that I am in dimension 1. So I have a single variable x. And the potential function v, which models the electric field, is essentially x squared times a constant, with k here a positive constant. And the differential operator that I have now, the Laplace operator, because I have one variable, it's simply this second derivative operator, d squared by dx squared. And so this is the operator that I have in hand. So this operator is called the harmonic oscillator. And finding its eigenvalues simply turns out to solving a differential equation, an ODE problem. So it's really the proof like this. To find all the eigenvalues, it's some kind of nice exercise in ODEs. And if we compare it with the classical mechanics, so I said that this is the quantum analog of the classical harmonic oscillator, because if you remember what the harmonic oscillator was, it was described by its total energy. So you have p squared here, the kinetic energy, and you have the potential energy here. And the force that forces the spring to oscillate is this attractive force, F equal minus kx. And if you look at it very precisely, you notice that it's simply the derivative of v prime, so the gradient of v. So that's why this model in quantum mechanics is called the harmonic oscillator, to respect the connection and its connections with classical mechanics. So now I will try present what are the eigenvalues of the differential operator, the harmonic oscillator. I'm pointing on it. And as I said, this is a simple ODE exercise to find these eigenvalues and eigenfunctions. So we find that we have a discrete set of eigenvalues. So we have an infinite number of eigenvalues, lambda 1, lambda 2, lambda 3, and so on. And the first eigenvalue, the lowest one, so these eigenvalues are arranged in decreasing order, the smallest and the one after it, and so on and so on. So the first one, the smallest one, lambda 1, it is h multiplied by a constant. So if you replace n by 1 here, you obtain lambda 1 equal to constant times h. While if you look at lambda 2, this to n minus 1, when you replace n by 2, it will be 3. And so there is a gap from lambda 1 to lambda 2. So lambda 2 is 3 times the same constant times h, and so on for lambda 3 and so on. All these eigenvalues are simple. They have multiplicity 1. That is, to each eigenvalue, there is essentially one eigenvector or eigenfunction, because here the eigenvectors are functions. There is one eigenfunction that comes from it. I can generate all the other eigenfunctions to this eigenvalue. So now I talk about the eigenfunctions. So to lambda n, there is a function phi n that solves this equation. And these functions are all given by Gaussians times polynomials. So the first eigenfunction phi 1, it produces all the eigenfunctions for the eigenvalue lambda 1. I'm pointing in, and it's a Gaussian. Phi 2, it produces all the eigenfunctions for the eigenvalue lambda 2, and it's a Gaussian times a polynomial, and so on. So it conserves this structure, a Gaussian function times a polynomial. And these polynomials are celebrated polynomials. They are the Hermite polynomials, in fact. So how this problem was solved, kind of guessing. So these eigenfunctions were guessed by decomposing this operator in a smart way. like solving the algebraic equation x squared plus 1 equal to 0. This equation, this differential operator was factored into two parts. And so the eigenvalues and eigenfunctions were constructed. And by a theorem and functional analysis, we proved that these phi n's, they form a dense subset, a dense subspace in the space L2, and that's why they are the only eigenfunctions. So let me comment once more about this, the particularity of this example. It tells a lot of things. First of all, it tells that the set of eigenvalues, the energy levels that I have, they are discrete. So I don't have a continuous set of energy levels. I don't have an interval. So I have a first energy level, a second energy level, and so on. The second thing is that the energy is small. So, and this is consistent with the atomic scale. So you see the energy is a multiple of h, and as I said, h is a small parameter, so the energy is very small. And the last thing is that the variation here, when x wants to, when I want to find that phi n of x here changes from one value to another, let's say if you want to see how phi n of x changes from 1 to 2, the change at the level of x will be something from square root of h to 2 square root of h. So the change at the level of x is very small. So if we want to change from one position to another, this will happen at a very small scale. So all that is consistent with the atomic scale we have in hand. Now, what about magnetic fields? So surprisingly, we will see that the example of the harmonic oscillator that described the energy levels for an electron moving in an electric field without magnetic field is the same operator that is going to describe a first model with, for an electron moving in a magnetic field. So for magnetic fields, these are modeled by magnetic potentials, by vector fields A appearing here. So here you think, if you are in dimension 1, you think of this gradient operator as the first derivative operator, d by dx. So if you take it squared, you get the second differential operator, d squared by dx squared. So what I'm going here is I'm perturbing it a bit. I'm adding a potential function here, A. And so when I do this perturbation, I think it's clear if you take A equal to 0, if you set this, you get the Laplace operator. So you get the magnetic effects disappear. But if you keep this perturbation in hand, what you get is that this Laplace operator that we saw previously and those additional terms. So remember, A is a vector field. And of course, we allow for an electric field as well. So it's present here in this problem. What is the magnetic field? I said that A is the magnetic potential. When it's present, it says that there is a magnetic field. So the magnetic field is a scalar function B if we are in 2 dimensions. So it's computed as the curl of the magnetic potential. So it's computed by this formula, assuming A1 and A2 are the components of the vector field A. So A is a vector field. It's a function from R2, valued in R2. So A is a vector function. So it has components A1 and A2. And A1 and A2 are functions as well. So we can compute this quantity, and this will be the magnetic field that we have. An important example of a magnetic field is a magnetic field which is uniform, which is constant everywhere. And this is given by a magnetic potential like this. So I'm going to write it on the board. So for the potential that I wrote on the board, which has first component equal to minus bx2 and the second component equal to 0, if I compute the curl by this formula, what I get is the constant function b, and this means that this is a constant magnetic field. It's uniform everywhere. So I want to inspect what happens with such a constant magnetic field in the absence of an electric field. So I consider this simplified operator. So I take A, the magnetic potential written there. So you notice the first component, negative bx2, the second component 0, and there is no V. And I get this Hamiltonian, or this operator. This is a very famous operator studied by Lando, and it's in honor of him, it's usually called as the Lando Hamiltonian. So this simple operator, where V is not present, it's 0, and A is taken in a very specific form, can be exactly solvable. What is exactly solvable? by the model of the harmonic oscillator, by the example of the harmonic oscillator I presented a while ago. So how we solve it, in fact. So if you know about the Fourier transform, what is the subject of the Fourier transform? When you introduce the Fourier transform, you change the operation of differentiation, the differential operator, the x1 here, to a multiplication by the frequency variable xi. So I will do a Fourier transformation with respect to the x1 variable, so that this differential operator appearing here will be replaced by its dual, by the dual variable, the frequency variable xi. And this way I can forget about the x1 as a differential operator. I can think of it as multiplication by a scalar. And so I forget about the differentiation with respect to x1 by the Fourier transform, and I get this operator. This operator now, what's nice about it, its differential expression depends on a single variable, x2. So it's like I get rid of one of the variables by the Fourier transform. So I have now an ordinary differential operator. So when I want to find the eigenvalues, I want to solve an ordinary differential equation. Much easier than solving a partial differential equation where several variables exist. And so that's the idea. So I get this operator. If you didn't forget the expression of the harmonic oscillator, it resembles it a bit here. So if I go to the harmonic oscillator, so it's h squared d squared by dx squared, a constant times x squared. So if I go to the magnetic Laplace operator and this special magnetic potential, and I do the Fourier transformation, I have a similar operator. So I have h squared dx2 squared and a potential term. Now this potential term is not exactly as in the harmonic oscillator, but I can reduce to it by doing a change of variable. So if I introduce the variable x as x2 plus p to the minus 1 times xi, so this term which I'm pointing on it now becomes x squared, and the derivative doesn't feel the change of variable because it's a linear change of variable. And so the dx2 squared, the partial differential operator here, becomes d squared by dx squared. And so I return back to the harmonic oscillator example with a constant b squared, with k equal to b squared, the constant that appeared before. And so I deduce that the energy levels are given by this formula, the same formula we've seen for the harmonic oscillator. So the energy level is levels are given by 2n minus 1b times h. So again, this is pleasant. Why? Because now I see how the magnetic field affects the energy levels. So the energy levels now are multiples of the small parameter amounting to the atomic scale h, the magnetic field strength b that I have, and the separation of the energy levels to n minus 1. So the harmonic oscillator is a very powerful operator because it describes magnetic effects as well. Now, sometimes we do confinement to bounded domains, usually called as quantum confinement. What's the problem? If you are familiar with PDEs, usually you see PDEs defined on bounded domains. If you are familiar a bit with spectral theory, you see that the operators are usually defined on bounded domains, while all the discussions and models discussed before were for the free space, not in a bounded domain. Why, in fact, we reduce to bounded domains? And quantum mechanics, that can be explained by quantum confinement. So if you remember, I said that the potential function V here describes electric effects. So it describes an electric field. So sometimes we can choose the electric field to do the confinement to a bounded domain. So if I consider such a magnetic, an electric potential phi, so it's the characteristic function of the complement of a domain omega. Omega is a bounded domain. So just let me remind you the definition. So I take V to be 1 outside the domain omega and 0 otherwise. This is the domain omega. And I will multiply by a parameter sigma. So if I consider such a V and I multiply by sigma, and I suppose that the electric field is infinity outside the domain omega that I have and negligible inside the domain omega. So that's the explanation of this kind of potential. So what happens when I send the strength of the electric field sigma, this new parameter that I introduced? What happens when I take it infinitely large? When I send it to plus infinity? What happens to the eigenvalue equation that I erased by accident? But it's written here. So what happens to the energy levels, let's say, when I have such a thing? So initially I have this operator in the free space. It has an eigenvalue. It has eigenvalues lambda n and with eigenfunctions un, solving this equation. So this function un, the eigenfunction, is defined in the whole space or plane. While if I consider the problem in the domain omega, I have this eigenvalue equation. So I have a function wn defined on omega only, not outside omega. And it satisfies this eigenvalue equation with T star. The limiting operator of this one is simply the Laplacian without an electric potential. So the difference between the eigenfunctions, that for un it's defined everywhere, for wn it's defined on a domain only. And of course, the eigenvalues are going to change because I have different eigenfunctions and I have different operators. So if we are very strict, we see that these two operators are independent and these two problems are independent. But in fact, this is not true, because when we send sigma to infinity, when we take the limit of this parameter sigma going to infinity, we recover from this problem I'm pointing on, this problem without an electric potential, which is somehow simpler. It's solving the equation Laplacian of wn equal to some energy level. And so these energy levels, they converge to these energy levels of this problem. And a boundary condition arises, which is natural in PDEs. So when we take this kind of limit, we observe a Dirichlet boundary condition on the boundary of the domain. So the precise statement is this one. So if I have lambda n or h sigma that depend on the eigenvalues of this operator, T sigma, when I send this parameter sigma to infinity, I find the eigenvalues of the operator T star appearing here. So I have this kind of convergence. And also the eigenfunctions, they converge to the corresponding eigenfunctions of the Laplace operator. So this kind of generating boundary conditions and doing confinement to bounded domains, doing quantum confinement. So in this way, it led to Dirichlet boundary condition, such that the function vanishes on the boundary, but I can select and construct other potential functions that lead to other boundary conditions, like the Neumann boundary condition, the Robin boundary condition, or other kind of delta type interactions. So that's why on the second part of the talk, I'm going to consider objects with that are quantumly confined in domains. That's why I'm going to specialize into bounded domains. So it's a kind, you can keep in mind that I have introduced an electric potential that led to such a confinement. Yes. Yeah. Yes, with a Dirichlet boundary condition. Yeah. If I want to recover Neumann or Robin, I have to add more complicated potential functions. So this is a classical result in the field. So from now on, I'm going to consider problems that are confined into bounded domains. So that's not something, that's not a purely mathematical object. It comes from physics by adding a kind of an electric potential that causes the confinement. And in this second part of the talk, I'm going to discuss magnetic fields in a more complex way, because if you look at the example that I presented at the beginning, the harmonic oscillator, and how it solved the problem of finding the energy levels in the absence of an electric potential when V is equal to 0, I neglected electric effects. Now, because I'm going to study objects defined on bounded domains, so I am considering electrical effects. So it's a more complicated problem. So because before I neglected V, I took V equal to 0. Now I'm going to take this term not equal to 0. And so it's not a surprise that I'm going to get a more complex problem. So I'm going to discuss this thing under a uniform magnetic field. The magnetic field is always constant in this part. So here I want to revisit the definition of the energy levels and the operator in more precise terms, because I have to solve a more complex problem. When I want to solve a more complex problem, I have to introduce objects very carefully in order to make use of the existing rigorous mathematical theorems in analysis and in spectral theory. So I have my domain omega and the plane. It's open, it's simply connected. I suppose that it doesn't have holes. That's the meaning of simply connected here. And I have a vector potential A as before. It lives in some space of a familiar space for PDE specialists, but you can ignore it. You can think that A is a function that you can compute its first derivatives, its first partial derivatives. So you can think of H1 here as C1, Ruiz notation, and its magnetic field is defined by the usual formula. I will assume that it is square integrable. And this is the operator I introduced before, the operator with magnetic field term. And if I consider a function satisfying the correct boundary conditions, and I look at the action of the operator and on such a function, and I take the inner product with the function itself, the inner product in the space L2, and I do integration by parts, I get from this expression this energy or quadratic form, usually called this term. So this term is very pleasant for two reasons. The first reason is that it's always a real number. I'm integrating the module of something, so it's a candidate to be an energy. The second reason is that I have derivatives of lower order compared to the operator. And the operator, I have derivatives of order 2. Here I have derivatives of order 1. And so this pleasant quantity, I will call it Q, because it's a quadratic form. And why this is important, because this will allow me to reconstruct the eigenvalues from linear algebra. So remember, linear algebra, it was the study of linear functions on finite dimensional spaces, let's say. So there are a lot of tools to compute the eigenvalues. So I want here to build up the eigenvalue for this complex problem by using linear algebra. How I do this? I pick a finite dimensional space M. So let's say that the dimension of M is 1, and I compute the energy, the quadratic form energy, and I normalize I divide by the norm of U squared, and I find the maximum when U varies on the space inside the space of dimension 1. What I get in this case is the first eigenvalue, lambda 1, but I have to pick the right M. So the optimal M is the space that contains the eigenfunction. So if I'm not lucky enough to pick the optimal M, the correct M, what I will get is an upper bound on the eigenvalue lambda 1. And in this way, when I want to compute limits, it's very useful to find upper bounds on the quantity I want to study. And I can repeat this. I can take spaces of dimension 2, and I maximize the same quantity. If I do not pick the right space with eigenfunctions, I get an upper bound on the eigenvalue lambda 2, and so on. So this formula is very important. It's called the min-max principle, and I understand it as a bridge between the study of eigenvalues in infinite dimensional spaces and those and linear algebra, finding the eigenvalues by the theory of matrices, by doing all the calculations on finite dimensional spaces. And at this level, I can explain the general strategy in such problems. So usually I have this quantity that I want to understand how it behaves when H tends to 0. So to get a rough idea about this quantity, we will pick M related to harmonic related to eigenfunctions of the harmonic oscillator, an example that we already understood, and play a bit with this so that to get a very precise upper bound on this eigenvalue. And the same thing, we do it for the lower bound, a kind of similar analysis. So the idea is somehow simple. And I'm going down to illustrate some examples, with some examples on this subject. So all these examples are new except the first one. So the first example is when I have the full plane R2. We've seen that this operator is the Lando Hamiltonian, and we understood the energy levels by the harmonic oscillator example. But what happens if I change the domain omega from R2 to the half plane? When I consider the half plane, I introduced a boundary. So it means I introduced a non-trivial electric term, V. So remember, each time I do confinement to a domain, I can understand it by a non-trivial term, V I introduced at the beginning. So the presence of this boundary means that I have a more complex problem. So in this case, the eigenvalues or the spectrum, if you want to call it. So now I have to use a more advanced mathematical terminology. So the set of eigenvalues is usually called the spectrum. The spectrum in this case of an operator and the half plane is now an interval. It's no more discrete. That's surprising because at the beginning I said that eigenvalues should do a discrete set. There should be a discrete set of values for the energy levels. It has an explanation that will appear later. The explanation is that it's like you considered one operator and it produced eigenvalues as discrete sets. And then very close to it, you introduced another operator and it held other eigenvalues. And you repeat this over and over. You get a bundle of operators and a bundle of eigenvalues, which are each bundle is or each fiber is a discrete set, but the bundle of all the discrete sets will be a continuous set, and that's why we see all the energy levels. They form this kind of continuous interval of an interval. So it's a complicated process, in fact, but and it's a gap for this model. So this model somehow it's not physically it's not very accurate physically because I don't see the splitting between the energy levels. So you can ignore what theta zero is. It's a kind of constant related to this kind of domain, half plane. And the dependence on H, the semi-classical parameter, is explicit. So I will skip some parts which are quite technical. And there is a third model, which is also an important model. Instead of taking the half plane, instead of taking a domain with a boundary, and the boundary is a flat boundary, we can take a domain which is a sector. So you have a flat boundary, but with a singularity here. So here you can understand that you have something like curvature equal to infinity. And for this model as well, you get that the essential spectrum, it's again a very complicated mathematical term for those who are not specialists in spectral theory. So it's, if you want, this is the ugly part of the spectrum, the part that we don't like to encounter in physics. It's the same as the spectrum we've seen in the half plane operator. So it's like if you consider this part alone, I'm pointing on, you can think of it as a half plane. So it gives you this the same spectrum as here, and the other part the same thing. And so there are left other parts of the spectrum, or there are left other eigenvalues that don't live here. And these are interesting eigenvalues because they correspond to energy levels in physics. And their existence is non-trivial. So for example, we can prove their existence for special values of the sector here. For example, for sectors that are acute, we have eigenvalues. So why I am talking about these things? Because I want now to go to bounded domains. So essentially, I can find two types of bounded domains. A bounded domain with a corner, like this one appearing here. And for this bounded domain, the energy levels are those we've seen for the sector, provided that those energy levels exist for the sector. So describing what happens as H tends to 0 is somehow simple. So I have a model problem, the sector problem, and I simply multiply by H and I generate the energy levels. But if I go to smooth domains, sorry, I have a very lengthy formula, but I can explain each term here how it arises. If I go to a smooth domain like this one, which you can understand it like a smooth version of the first one. So here you have this vertex, this corner, here you have you have a smooth, you smoothened the domain. So this domain will be distinguished by this point where the curvature is maximum. So here the domain is curved the most, the curvature is maximum. And you can neglect all what happens inside the domain and focus only on the geometry of the boundary. And so this boundary, as you see, is a smooth curve. It can be parameterized by the arc length. So when you consider 2 points on the boundary, you can measure the distance between them as the arc length distance. And when you introduce this arc length distance, you can see the curvature as a function on the boundary. And for this special type of domain, the curvature will have a unique point of maximum curvature. So it's this point here. So it's like an egg domain, as you see. And what happens when I send h to 0? So I see a first term, which is independent of m for the nth energy level. But you see a constant. This constant is the constant for the flat boundary. So it's like you ignore all curvature effects and you think of your domain having a flat boundary. And that's why you see this first constant theta 0. Then when you want to introduce curvature effects, when you want to introduce the geometry of the boundary, you get this second term. But unfortunately, this second term doesn't depend on m. This means that finding the energy level is very complicated. So flat boundaries are not enough, considering the curvature effects is also not enough. It gives me the curvature contribution, but it doesn't give me the separation between the eigenvalues. So it's until the last term that we see a quantity that is similar to what we've seen for the harmonic oscillator. And this is not by accident. So 2n minus 1 times the power of h times constants. So here we see the splitting. So this means that the analysis will go in 3 steps. The first step is to compare with a flat boundary. And then you improve the computations and you include the curvatures of the boundary and you get the second term. And then you have to do a very delicate analysis to see the effective operator, if you want, the operator that acts on the S variable. And this will be a harmonic oscillator at the end. And that's why we see this kind of object. Why things are complicated in mathematics? Because this is very hidden. So it's not after 1 layer or 2 layers. It's after 3 layers that we get the splitting of the eigenvalues. So it's no surprise that the proof of this theorem is very hard and it required pseudo-differential calculus. When I have revisited this theorem in the setting of a magnetic edge that I will talk about it briefly later on, I found a proof with Bernard Helffer, which is also an author of this first result using pseudo-differential calculus, and Assaad. We found a proof without using pseudo-differential calculus. And that means what? It means that if you don't know pseudo-differential calculus, you can still be optimistic and visit these kind of problems. So I forgot to mention something that for both results here, I considered the Neumann boundary condition. If I consider Dirichlet boundary condition, I force eigenfunctions to satisfy the condition to vanish on the boundary, then the story is completely different and you get terms as complex as this one. So now I'm left with 10 minutes maybe to talk about the magnetic edge. So what's the story of the magnetic edge? So experimentally, magnetic fields were constructed to vary very quickly. So if you look at this first example, so the magnetic field in this zone is A, and on the zone on the right, it's 1, and A is not equal to 1. So there is a jump that happened along this, across this edge, across the x2 axis. So that's why we call this a magnetic edge. So these magnetic fields are modeled as step functions. So in practice, in reality, they are not step functions. They vary smoothly from one zone to the other. But a mathematical model that is consistent with experiments is to take them as simple functions. And if I want to analyze this simple model where the edge is flat, I get that the spectrum is similar to the models I discussed before about uniform magnetic fields on a half plane with a flat boundary. So you see that there is this interval with this new constant beta A. This new constant beta A is the quantity describing the presence of the magnetic edge, if you want. And if you consider a magnetic edge on a domain with a flat boundary, so I'm pointing on the boundary now, and what is marked here in red is the edge, you get something also similar to what we've seen for sectors before. So you get that the essential spectrum, the ugly part of the spectrum, is the same as we've seen here, with the presence of eigenvalues. And I will skip the definition of these objects. So I will skip them, and I will go to the problem of interest here. So I have this kind of domain. And I am free to choose Dirichlet boundary condition, look for eigenfunctions satisfying Dirichlet boundary conditions on the boundary, or Neumann boundary conditions. I will show you that Dirichlet boundary condition here will give us a richer structure. If I suppose that I have a Neumann boundary condition, and I suppose that I have this kind of curve here that makes an angle alpha with the boundary and an angle beta, with the other part of the boundary. And I suppose that I have a magnetic field, which is 1 on the right and A not equal to 1 on the left. So if I suppose that the boundary condition is the Neumann boundary condition, I'll get that what describes the splitting of the energy levels of the eigenvalues is the model. Is this happened? Oh, no. You get this model, in fact, sorry. It's described by this model in a simple relation. But if I consider Dirichlet boundary condition, I mean, I look for eigenfunctions satisfying the Dirichlet boundary condition here and to the energy levels, I find a formula similar to the formula present in a bounded domain. And I find a more complex eigenvalue splitting. The first term, it corresponds to the model with a flat edge, no contribution of the curvature. The second term, it corresponds to where I put an arrow here, the point where there is a deformation of the curve gamma that separates the values of the magnetic field. And at the end, at the third level, I see the splitting of the eigenvalues. So the proof that we wrote here, it applies to the case of bounded domains. And it's interesting because it doesn't contain pseudo-differential calculus. Let me do one more comment. Why this problem is slightly, from a physics point of view, somehow more interesting than the other problem, or slightly different from the other problem, let me say. Because for the other problem, when I considered confinement inside the domain omega, that means that I introduced an electric field, a special electric potential. While here, the confinement to this edge is produced purely by the magnetic field. So it's like the first example I presented, the Lando Hamiltonian, but instead of considering a magnetic field which is constant everywhere, I considered a magnetic field that is a step function and that it has got discontinuity along a non-flat curve like this, and this produces this kind of new magnetic effect. About the proof, I will not take you into the complicated expressions here, but the idea is to express the operator in coordinates along the curve gamma. Think of them like polar coordinates for the disk domain, and to express the operator with these coordinates, and then expand the operator as a formal quantity in powers of h. And this is where I'm pointing here. And when you look at the expansion of these quantities, you get the model with a flat boundary, a model that contains the curvature, and a last model that contains the harmonic oscillator here, this last expression. And this is the intuition behind finding the harmonic oscillator everywhere in such computations. About the proofs are in two parts. Finding upper bounds, these are easy, because as I explained at the beginning, you select the subspace M in the min-max formula in some way that respects this decomposition, and you produce upper bounds. But when you want to find lower bounds, you need to understand what happens to the true eigenfunctions. So you need to understand how the true eigenfunctions behave. So you need to understand the qualitative behavior of a solution of a PDE, and that's a difficult problem usually. And what we expect is that this eigenfunction should have a product structure. The variables should be separated. So a phase term, a pure phase term, exponential I zeta as, times an eigenfunction of a 1D operator. And to start getting results consistent with this formula is to get these two estimates here. So if you compute the derivative with respect to S here, what you will get I zeta A times phi A. So what I write here as an inequality or as an estimate is consistent with this, because when I compute the derivative with respect to us here, if you obey this structure, I get that this quantity is very small, and this is what is stated here. And it can be left to the higher order. It can be iterated and prove it to second order as well. I consider derivatives of second order. So these two inequalities are usually obtained by pseudo-differential calculus. Here they are obtained by a PDE proof. It's a lengthy proof, but it doesn't require to know the theory of pseudo-differential calculus. And that's why that was the main motivation for me, for example, to apply this method to this problem, to understand how we can overcome pseudo-differential calculus. So here are some comments on how to select the spaces correctly and get a lower bound in the min-max formula. I will skip this. And I will do a brief comment on the literature. So the story is very old, in fact. So some colleagues in 2016 advanced the study of this problem by doing magnetic WKB constructions. And quite recently, they solved a very difficult problem. So here I discussed what happens when I have a single point of maximum curvature. What about if I consider an ellipse? A symmetric domain. So there I get a tunneling effect. So it means that the splitting between the eigenvalues occurs at a very small scale, at an exponentially small scale. So that was solved recently. And in 2015, San and Nicolas Raymond, they used the symplectic geometry to address the spectral theory problem considered here from the symplectic geometry angle, and they obtained some connection with classical mechanics. So by contribution, if you want, I revisited the same problem, but with very simple tools. And as a matter of application of all these contributions and the result I presented today with Soren Fournet and Bernard Helffer, we considered a symmetric magnetic edge, and we proved that we can compute a splitting of eigenvalues occurring at a very small scale, and that was will appear in a volume celebrating the 90th birthday of Elliott Leib. If you want to talk about 3D domains, there are contributions by Emmanuel Giacomelli and Wafa Assaad, and for the magnetic edge problem, and for the problem in a smooth domain, but with corners and edge wedges, it's by Bonayi, Noel, Doge, and Popov. And if you want to discuss it in the context of superconductivity, magnetic edges are also interesting. So the story of studying magnetic edges started from there. At least my story with magnetic edges started from there. And there are many open questions left. For example, if I take a magnetic field that is perfectly symmetric, it's -1 on the left and +1 on the right. So the story becomes completely different. It's a work in progress. And what happens if I consider the magnetic wall? I mean, a magnetic field which is negligible on one side and one on the other side. That's also an open problem that I am wishing to see its solution by me or by someone else. So I can stop here. I'm sorry for the complicated formulas at the end.
Thank you very much. Thank you. We certainly have time for questions. Yes, yeah. You can use the microphone if you want. Press it.
So if you change the sharp edge, so your electric field into a smooth function that goes from 0 to 1, but in a smooth way, does it change dramatically? What happens? Or
so the gradient of the function will enter to the play now, right? So we'll see a gradient of the function. So if you want, for this problem, it's like the gradient, it's some negative power of h, and h tends to 0. So you can connect it with this problem by considering a gradient that behaves in this way. But if you want to consider a gradient that varies on the length scale, on a constant length scale, there are results from this thing, on this situation. There are results, but let me remember one of them. I contributed to this in the context of nonlinear analysis. If you want the model operator occurring here, it will be more complicated. So here you see the potential function. It's a linear function on every side. For such models that you propose, you will see something like tau squared here. inside the expression, and it's more difficult at somehow. From certain angles, it's more difficult. But this situation, its interest is that it's experimentally observed. I mean, they were able to construct such magnetic steps, if you want. The other question you are asking is somehow more related when you consider 3D domains. So magnetic fields on it, if you consider a uniform magnetic field, a constant magnetic field on a 3D domain, it's going to, the surface of the domain will feel it as a magnetic field that vanishes in the manner you are mentioning.
Is there something like if you have a sequence of functions, smooth functions that converge to step function, then the behavior somehow?
Yes, you can prove that. Yes, so your question, Siamak, is I consider a sequence of magnetic fields that depends on M, and this sequence varies on it's a smooth function. Every term of the sequence is a smooth function, and I want to see in the limit this sequence tends to a step function in some L2 space, let's say. So what happens to the energy levels? At order 1, they will converge to the energy levels of the step function model at the first level. But when you want to consider the splitting and other things, maybe things will be more complicated.
Question? Yeah, Christian?
Yes. My question is, why are you saying you want to avoid pseudo-differential calculus?
I expected this question because it's a very powerful tool, let's say. Pseudo-differential calculus is a very powerful tool. But if someone like me doesn't understand, master the pseudo-differential calculus very well, I like to see a proof without pseudo-differential calculus. It's more elementary, if you want. So that's the reason.
You might say that it will take a long time for you to understand the pseudo-differential machinery.
So if you want, you can prove the same theorems by pseudo-differential calculus employed into this. And I have worked on this in collaboration with Nicolas Raimond, but it's not me who did the pseudo-differential calculus. But what happens then, if I want to explain to students, if you want, or to beginners, I have to explain something like 300 pages of admitted theorems to start with. They have to admit the proofs of 300 pages to start using them with confidence. I mean, so just as that's the only thing. I mean, but don't you think that it's nice to see two proofs, one by pseudo-differential calculus and now one that doesn't use pseudo-differential calculus?
Me, I think yes, it's nice.
Yeah. I mean,
Two different perspectives.
Pseudo nice, yes. You can see something like that. Yeah, but I mean, for example, I don't master pseudo-differential calculus very well, and I want to. If you want to find the results quickly for other questions related to this one. So I was happy to see a proof without pseudo-differential calculus, a less complicated proof if you want. I mean, that relies only on integration by parts and smarter tricks. It relies only, if you want, on the Fourier transform, on playing with the Fourier transform, not employing this more general class of symbols.
Okay, and I have another question. So why, when you pass to a domain, you don't no longer have a discrete set of eigenvalues?
I'm not sure I've got exactly your question, but I think you are talking about here.
When you impose a Dirichlet condition, for example, you explain that the spectrum is basically some open interval on the right and left interval.
So the open interval, you mean, for example, about this thing here, what I'm pointing, about this result?
Yes. Yeah. So why do you expect that we do no longer have a discrete set of eigenvalues? So because usually, from what I understand, I mean, it's discrete because there are a lot of constraints. So
Yeah.
if it's continuous, I mean, then it basically means there are fewer constraints, no?
So the reason, there is a technical reason behind this. So discrete spectrum is usually related to compact operators.
Yes.
Yeah. So when you have an unbounded operator like here, you expect you are looking for an operator with compact resolvent. So you are looking for some compact embedding of a Sobolev space inside L2, inside the space of square integrable functions. For this space on the unbounded half plane, you don't have the compact embedding in hand. So that's what explains technically why we can't find the discrete spectrum. Now, if you want to get...
Would you say that you have a fewer constraints, basically?
A few?
You have a fewer constraints.
Fewer constraints. What I am lacking here is the compactness, if you want. So the boundedness of the domain, it imposes compactness. So you can understand it as a constraint if you want. But here I don't have something that give me the compact embedding of the Sobolev space into L2, and that's why I lose the operator with compact resolvent. I lose the compact operator. But what happens for this specific operator, in fact, when you do the Fourier transform and observe that for every psi, you have this operator appearing here, I am pointing on it. So the eigenvalue, or the first eigenvalue of this operator, I am pointing on it, this is a 1D operator, will be denoted by mu of psi. This one is, the spectrum of this operator I'm pointing on is discrete. But then you have to consider the spectrum of this operator for psi equal 1, then for psi equal 1.01, and so on. So you get a bundle of spectra. And this bundle of spectra add together and they give you the continuous spectrum in hand. So when you go to the bounded domain, this thing is a kind of fibered here. So I still have the same thing, the same constants, but it's like I have a first eigenvalue, then a second one, very close, very, very close to it at a distance h to the -1, and so on and so on. They pack together as an interval, but they are still separated. But
basically here you have the asymptotic expansion, correct?
Yeah. But if you consider, for example, a disk domain, you can do separation of variables with the Fourier transform and do everything to a very great details. And there you will see that, for example, if you replace this model with the disk, it has a constant curvature as here. It has some kind of flat geometry if you want, because the curvature is constant. But you will see fewer xi's here because this psi comes from the Fourier transform on all the space. If you consider, for example, the Fourier transform on the circle, then the Fourier modes will be a discrete set. But they are packed near each other, dependent on H.
So for example, on R plus, what do you do? So on R plus.
On R plus,
you use some kind of Fourier transform, but
so I am using here the Fourier transform.
Adapted Fourier transform.
I am using here the Fourier transform on R because I am doing it with the x1 variable, the variable that lives on R, and the x2 variable is this variable tau. It lives on R plus.
But you can maybe there are some kind of modified Fourier transform on R plus. No?
I agree, but I didn't use it here. I mean,
so what
if you want the link between this, I go to the. Suppose you have a very large circle.
Okay.
So the spectrum will be something like this thing. It's discrete. The spectrum will be something of this form. When you take the circle larger and larger and larger, these eigenvalues are going to live very close to each other. So if you take the limit as h tends to 0, you will not see the difference between them, and they will fill all the interval h theta 0 plus infinity. So it's like they form a dense subset, if you want, inside this continuous spectrum. Yeah. And I can give you one more comment. Just if you look at the structure of eigenfunctions here, of perfect eigenfunctions here, so they are not square integrable with respect to us. So here, so this part is an L2 with respect to tau, but with respect to us, you can't integrate it over all of R. So that means that the eigenfunctions they escape from the Sobolev space. If you are in a bounded domain, this S will live inside a bounded interval, and then you get that the eigenfunctions are square integrable, and you get that discrete spectrum if you want.
Hi, so I'd like to understand, you have some work with George Habib.
Yes.
And I want to know whether it's disconnected or there is a way that you actually put it in this story.
Yes, so let me remember that work. So that work was about magnetic fields, about two things, in fact. So it was about magnetic fields that are zero everywhere except on a single point. Okay. It's infinity. So we call such things as magnetic fluxes. So the point was to know if you don't have a magnetic field at all and you have the Neumann boundary condition, the first eigenvalue will be trivial. It will be zero. It will be null. If you add a magnetic potential, not a magnetic field, I mean a magnetic potential A, if you add a magnetic potential A whose curl is equal to zero everywhere except at a single point, this will be called a magnetic flux. So adding it will increase the eigenvalue, though I will have an eigenvalue not equal to zero. So that was solved for the Neumann problem, and George asked me the question, what happens for the Robin problem? And by a comparison argument, we were able to write the same necessary and sufficient conditions for the Neumann problem to say that the eigenvalue with a magnetic potential with a magnetic flux is going to increase. So that was one part of the work. The other part was about curvature effects, but in a non-asymptotic regime, and about the splitting of the first and second eigenvalues. So for weak magnetic fields. So now I can answer your question very precisely because now I remember what we did in that work. So we considered the problem without a magnetic field at all. And there is a spectral gap for the Laplacian between the first and second eigenvalue. We added a magnetic field with intensity V, and this V is very small. And we want to see a non-asymptotic statement saying that this kind of splitting will continue to occur. So it's something like we found a bound on V related to the geometry, to the curvature on the manifold and the other things. And we proved that the gap still exists for the Robin problem. So the contribution for Neumann was understood, but we approached this for the Robin problem. Here, if you want, the link with this problem here is the regime of very large magnetic field, because if you do a simple change of scales, it's the same as taking the magnetic field B tending to infinity and H equal to 1. So they are complementary, not with respect to the methods, but from this angle, somehow complementary.
Nice, thanks.
Thank you.
I have a couple of questions.
Yes.
So for the computational physicists in the audience, what computational physicists in the audience, what is an interesting direction to proceed based on the limits that you have considered? And how difficult do you imagine the work to be?
So my colleague Virginie Bonaille-Noël, she is a numerician as well. She did the numerical computations for this sector problem. So this sector problem is still not completely solved theoretically. She did computations, for example, proving that the energy, the lowest energy, is a monotone function with respect to the opening of the sector alpha. For the same problem, for example, so the work that Wafa started here for the magnetic steps where we have something similar to a sector. So I know that when alpha is equal to pi over 2, a right sector, I know exactly what happens here by symmetry arguments. But what about when alpha goes to 0 or it moves? So it's not so clear what happens here. So numerical computations here are completely absent, for example. So another thing that we can look for is this problem. What happens for A equal to 0 or A positive? So that's also something that we don't know a satisfactory theoretical answer about it. So it can be of interest from a computational point of view.
So worth pursuing.
Worth
pursuing.
Yeah. So
I also took note of the remark you made about the role of curvature in creating the harmonic well. Does one understand the tunneling case as actually giving rise to two wells and a transition between them?
Exactly.
The tunneling we're talking about?
Exactly. So for the story of tunneling, for the Neumann problem, yes, it's caused by the geometry, if you want. So you have so it can be proved theoretically that when you have a smooth domain at the points of maximum curvature, these are wells. If these wells are symmetric, then you expect tunneling to occur. An upper bound on tunneling is already known, since very old works, But to prove the lower bound, the existence of the splitting in this situation, it was very complicated. And it was really a long project, so solved just recently by Nicolas and his colleagues. But if you want, we proved with Fournet and Helffer, we proved another example of tunneling based on their tools, of course, on their proof, is that tunneling is induced by the magnetic field itself. So you don't include magnetic electric potentials and so on. So you can fabricate magnetic fields. At least now, theoretically, we have examples of magnetic fields that produce this kind of tunneling.
What is the type of variation you have to allow for?
Type of variations at what level?
In this case, tunneling results from the shape of the domain. Here you're saying we don't touch the domain, it's probably a disk or something. And then what do you do with the magnetic field?
So I consider the full space, and I consider a magnetic edge, a curve where the magnetic field has a discontinuity along it. And I consider this edge to be symmetric, for example, an ellipse or so on. So it means that it's possible to generate tunneling purely by the magnetic field. So mathematically, it's not a big deal here. So besides the work we've done in this paper and the other works by Nicolas, so we just adapted the things together. But from a physics perspective, probably this is the first example of a magnetic field induced, a purely magnetic field induced tunnel effect. And I guess Soren was after the idea. So he said that he pointed our attention that examples of purely magnetic field, purely magnetic tunneling effects are worthy to explicitly pointing them. But for the other curvature effects, because this hybrid mode prevented me from using both precisely. So we have this domain, and there is an important model of the disk. So look what happens with this tangent disk here. The radius of this tangent disk is the same as the curvature. So you understand this model very well, which explains it's related to the question of this as well. Explains why we have this pair of eigenvalues, because we have that. The real model to compare with is this here, and you keep this rolling over the boundary and everywhere you have to this radius. Consider you maximize or you minimize the negative term, so you minimize while maximizing the curvature.
That's a nice picture. Okay. Please join me in thanking Ayman again for inaugurating our series. Thank you very much, Ayman. Nice walkthrough to beautiful mathematics. Thank you.
Thank you very much. And again, I would like to thank you all for your for attending this lecture and for the questions and for the comments. I'm looking forward to the other lectures in this series.
Yes,
see
so
them.
we'll continue with presentations by CAMS fellows following later in April and in May. We will have a colloquium on Thursday, which is a wide public talk on complexity and nonlinear phenomena by our visitor in the physics department. And then we will also inform you of a course and another colloquium by Atia fellow, who will be joining us towards the third week of April. So lots to look forward to, and I thank you all for your interest and support. Thank you very much. Okay.
Welcome.